Today we're starting chapter 7. We are going to be simplifying nth roots today. So before we've simplified square roots, maybe every now and then cube roots. Today we will do more roots. All right. I don't think anything on the screen is going to be a surprise to anybody. Since 5 squared is equal to 25, 5 is the square root of 25. Since 5 cubed is 125, 5 is the cube root of 125. Similarly, since 5 to the 4th power is 625, 5 is the 4th root of 625. So our definition here for any real numbers a and b and any positive integer n, if a to the n is equal to b, then a is the nth root of b. So instead of just taking square roots, we are now also going to take cube roots, 4th roots, and other roots. It's the same idea as taking a square root. So if we go back to the top one, when we're finding the square root of 25, when we were taking the square root of a number, if we didn't already know it was a perfect square, we made a factor tree. So for 25, we would break it into 5 and 5, and we looked for pairs of numbers. So we had a pair of 5s. We looked for 2 of the same number because we were taking the square root. If you're taking the cube root, you'd be looking for 3 of the same number. Or the 4th root, you'd be looking for 4 of the same number. So it's the same idea, we're just looking for more than just a pair now. We're looking for 3 or 4, whatever they tell us. When asked to find roots, even roots have 2 answers. We've talked about that. When we take a square root, we had a positive and a negative. Odd roots, so like a cube root, the 3rd root, the 5th root, odd roots have only 1 real answer. There are 2, but only 1 is considered real, like a real number. All right, so let's talk about some examples. First one, find all the square roots of 196. So square roots we've done before. We take the square root of 196. What do we get? $14 or negative 14. So we usually put the plus or minus out in front. Okay, so for the square root of 196, we get 2 roots because the square root is an even number. So we'd get plus or minus 14. All right, the second one, find all the cube roots of 8. So the cube root, which we'll talk about how to write this in a minute, the cube root of 8 means I'm looking for how many of the same number to multiply to 8. 3 of them. Okay, I need 3 of the same number to equal 8.
2.
Good, so that would be 2. 2 times 2 times 2 is 8. Okay, but the note said that we could have a real one for an odd number, right? There were actually 2 answers. One was real, and the other one was not real. Does anyone think that they would know? Well, we'll leave it at that for now. Are we all okay with 2? No, because 4 times 4 times 4 would not equal 8. So let's just leave it at the real one for now. We'll just leave it there. We all understand why 2 is a cube root of 8? Okay, let's just leave it at that for now. All right, what about the cube roots of negative 1,000? Negative 10, good. Because negative 10 times negative 10 times negative 10 would equal negative 1,000. So that's why negative 10 would be the cube root of negative 1,000. Questions on those examples before we move on? Are we okay with the difference between squares, cubes, and fourth roots? Okay. All right, here is where we see the terminology. So this diagram is what's supposed to go in that box in your notes. Okay, if we're taking the nth root, n is called the index. It sits kind of right outside or sometimes inside the little pocket of the radical symbol. Okay, so either right above or right inside that little pocket is where your index goes. That's what's telling you what root you're taking. When we're taking a square root, we don't usually put a 2 there. So if you're taking a square root, the index is implied to be a 2 or understood to be a 2. But if there's another number written there like a 3 or a 4 or a 5 or some other index, that's what's telling you what root you're taking. Okay, we still have the radical symbol. We're familiar with that. And I believe we have seen the term radicand at least once in here before. That refers to whatever is underneath the radical symbol. Okay, off to the side, you've got another box with some blanks. When a number has 2 real roots, the positive root is called the principal root, and the radical sign indicates just the principal root. So oftentimes, if you're just given a problem, like down at the very bottom, it says the fourth root of 16, we would just put 2. If you put plus or minus 2, that's not wrong, but usually for an even root, we are just implying that we want the positive. Okay, that changes when we're finding solutions to polynomials like we did last chapter. But in general, if we're just taking a even root, we just want the positive answer or the principal root. All right, on this next set of examples, we are finding each real root. This is similar to what we were doing in examples 1 through 4, but instead of it being written out in words, they wrote it in symbols. So what root are we trying to find on number 5? The third root, or the cube root. How do we know that? Okay, the index is a 3. So that means we're taking the cube root of negative 8. What's the cube root of negative 8?
Negative 2.
Good, negative 2. Okay, we'll go to the side for number 6. What root are we taking on number 6?
4.
The fourth root of 81. Now again, if you're not sure what it is, take 81 and make a factor tree. What can we break 81 into? 9 and 9. The 9s break into 3 and 3 and 3 and 3. If we're taking the fourth root, we are looking for how many of the same number? 4. So we're looking for groups of 4. There it is. We've got a group of 4 3s. So the fourth root of 81 equals 3. Now if you put plus or minus 3, that's not wrong, but like the last slide said, generally when we take an even root, we just care about the principal root or the positive one. All right, number 7 should be easy for us. What root are we taking on 7? The square root. Okay, if there's nothing written in the index, it's understood to be a square root. What's the square root of 49? 7. Again, if you put plus or minus 7, kind of out of habit, that's fine. But we just really care about the principal root. On number 8, which root are we taking? The square root. What is the square root of negative 16?
4.
4i.
What do the directions say on this slide?
Find real root.
Find each real root. Is 4i a real root?
No.
No, because I is imaginary or complex, so there is none. There is no real root. So you could put none or put no real root. If it asks for all roots or any root, then you could use the 4i. But if it says specifically a real root, and the only possible answer you have is to use an I, there's no real root. Do we have questions about that? Okay. On number 9, what root are we taking? Third root or cube root, whichever way you want to say it. The cube root of negative 27 is negative 3. Good. Okay, if you're taking an odd root of a negative number, your answer will be negative. All right, our next set of examples involves simplifying radical expressions that involve variables. So our helpful hint is to break apart the expression into perfect root parts. I'll show you another way of what I call just expanding it. On number 10, what root are we taking? The square root. Okay, if there's nothing written in the index, it's understood to be a 2, meaning we're taking the square root. So if you want, you can break this into the square root of 4 times the square root of x to the 6th. If it helps you to think about the number separate from the variable, that's fine. Break it up like that. What's the square root of 4? 2. Okay, times, if we are taking the square root of x to the 6th, there are different ways of thinking about this. One way is to think about it fully expanded. X to the 6th means we have how many x's multiplied together? 6 of them. And if I'm taking the square root, I'm looking for how many at a time? 2 at a time. 1, 2, 3 pairs. Are we all okay with how there are 3 pairs? Okay, so every time we have a pair, one of those goes out. So how many x's are coming out? 3 of them. 1 from each pair. Do we have anything left under the radical? No, we used all of them up. There's nothing left. How would we rewrite 2 times x times x times x?
2x to the 3rd.
Good, 2x to the 3rd. Another way that people like to think about this would be to divide the exponent by the index. So our index in this case is 2. Our exponent is 6. 6 divided by 2 is 3. Okay, so that can be a helpful hint. If it doesn't divide evenly and you have a remainder, that's when it gets a little tricky. Okay, on number 11, what root are we taking? The third root or the cube root, which means we're looking for groups of 3. So if we want to write this out expanded, we would have a times a times a times b times b times b times b times b times b. Okay, 3 a's, 6 b's. Are we all okay with how I came up with that? And we said we're looking for groups of 3 because we're taking a cube root. So we got a group of 3 a's. We have a group of 3 b's. We have another group of 3 b's. For every group, how many comes out?
2.
No. 1. For every group you make, only one of them can come outside. So for this group of A's, 1A can come outside. For this group of B's in the middle, 1B can come outside. And for this group of B's on the end, 1B can come outside. Is there anything left inside? No, we used up everything. And how would we rewrite A times B times B? AB squared. Are we talking about the 3 that's right here?
Yeah.
Okay, that 3 is our index. It belongs with the radical. So if our radical is gone, so is the index. Now there's a difference if we have like a big 3 out in front of the radical. Okay, that 3, the big 3, that would have to stay as part of our answer. Okay, so if you have a big number outside your radical, then yes, that number stays. But the little 3 that's our index stays with the radical. So if the radical goes away, so does the index. Does that make sense, the difference between those?
Yeah.
Okay. Other questions? Okay, are we ready for more examples? All right, I'll give you a minute to copy these down and maybe try the first couple on your own. Make sure you're paying attention to your index to know which route you're taking. I think that you should be capable of getting through 15 on your own for sure. 16 and 17 get a little tricky, but we'll talk about all of them in just a minute. Can anyone let me know what they got on number 12? Jacob?
XY squared.
Very good. XY squared. So remember, we can either expand it and make groups. We would have one group of 4 x's, 2 different groups of 4 y's. We're taking the 4th root. That's why we're looking for groups of 4. The shortcut way would be to divide your exponent by your index. So 4 divided by 4 is 1. We don't usually write an exponent of 1. 8 divided by 4 is 2. All right, who can help me out with 13? Emily?
2xy squared.
Good, 2xy squared. We're taking the square root. The square root of 4 is 2. The square root of x squared is x. And the square root of y to the 4th is y squared. Again, if we're taking a square root, we don't write the index usually, but we understand it to be a 2. So you can still do the division rule with your exponents. 2 divided by 2 is 1. 4 divided by 2 is 2. Does anyone have an answer for number 14? Sadia?
3c squared.
Really close.
Oh, negative 3c squared. Sorry.
Good. Negative 3c squared. So the cube root of negative 27 is a negative 3. And again, 6 divided by 3 is 2. That's how we got the c squared. If it makes more sense to you to expand it and write c times c 6 times and find your groups, that's fine. But I'm going to recommend picking up on that shortcut. It'll help you out in the future, save you some time. Who has an answer to 15? Charles?
X squared, Y cubed.
Good. X squared, y cubed. Okay, we're taking the 4th root. 8 divided by 4 is 2. 12 divided by 4 is 3. All right, who has an answer for 16? Sadia?
X, well, parentheses, y plus 2 cubed.
Good. I would agree with that. So, what this 6th power means is that we have 6 sets of parentheses called y plus 2. So that would be a lot to write it out. Y plus 2, y plus 2, y plus 2. Okay, 6 times. we're taking the square root, so we're looking for groups of 2, and we would have 3 groups of 2 sets of parentheses. The easier way to think about it is, again, to use the division. 6 divided by 2 is 3. Just leave what's in the parentheses inside of parentheses when it's like that. Questions about 16? Caden?
Wait, I had that number outside is 2.
So if it's a square root, meaning they didn't put a number there, we understand it to be a square root, and it's a 2. So if you want to write a little 2 on square roots to help you remember that, that's fine. When you don't see a number written in the index, we know it's a 2. Does anybody think they have an answer for 17? Charles, what do you think? Sadia, do you have another answer?
Y.
Just y. Okay, so if we're using the whole division thing, right? We're taking our whole exponent divided by our whole index. Our exponent is 3x and our index is 3x. If you take something divided by itself, what does it become? 1. So that becomes our new exponent, y to the first, or just y. So I would agree with just y. The x from the exponent and the index are also going to cancel each other out just like the 3's did. Questions about 17? So 17 is one where that whole division property comes in handy. I think that is it for our notes.